Hello students, welcome once again back to the learning management system of the Department of Collegiate and Technical Education. So you all know that we've been involved in the discussion on mixing and agitation since the last two classes. So this is the last unit of the syllabus in which we are learning the unit operations, mixing and agitation, and the equipments used in these two unit operations. So let me just take you back briefly to the topics learned in the last class. So this exercise is important because I believe that since the discussion is continuous, so whatever that you learned in the previous class, uh, that will help you in the understanding of the present class topics also. So these are the things that you learned in the last class. We discussed about the turbine type impellers, the various designs of turbine type impellers, the constructional and operational details, and what kind of flow patterns the turbine type impellers create in a agitated vessel. So today's class discussion is about paddle type impellers, their construction and operational features, then what are the flow patterns that are created in agitated vessels. So paddle agitators with the 2 or 4 blades are usually common in agitated vessels. So they consist of blades which are vertical, that is parallel to the axis of the shaft, and usually they extend close to the vessel wall. See, if you can look at any of these designs, you can see that the paddle agitator blades are almost closer to the wall of the vessel. Okay, so these are the different kinds of designs used for specific applications using of paddle agitators. So the main characteristic of a paddle agitator are they are simply pushes, means they don't create any kind of rigorous mixing that you have seen in case of turbines or propellers. So they simply cause the liquid mass to rotate in a laminar swirling motion. Practically, no radial flow and no axial flow can be seen in a paddle agitated vessels. So the circulation in with this kind of agitators is very poor and mixing action is not that sufficient. So these are meant for creating a simple motion with a low speed of around 20 to 150 rpm. The total length of the impeller lies between 50 to 8% of the inside diameter of the vessel. So it is commonly 80% of the diameter. So that is the reason why its blades are almost close to the wall of the vessel. Those are some of the constructional details of the paddle agitator. Let's continue again. So the width of the blade is around 1/4 to 1/10 of the paddle diameter. So the width means this width. So this width will be about 1/4 to 1/8 of the agitator diameter. In some designs, the shape of the blade is similar to the shape of the bottom of the vessel, as you can make out in the second, third, and fourth figure. It is B, C, and D. The shape of the agitator blade, that is the impeller, is similar to the shape that is inside shape of the vessel. So that means this entire periphery of the agitator is almost close to the wall of the vessel in the given agitated vessel. So this will have a close clearance with the wall of the agitated vessel. So that kind of construction is given to paddle agitator so that it moves over the surface during its operation. So thereby it keeps scraping the surface and prevent any kind of deposition that can occur on the inside surface of the agitated vessel. So such type of paddle is known as anchor agitator as shown in diagram 2. The anchor agitators are useful in preventing deposits on a heat transfer surface as in reaction vessels and are commonly employed for obtaining improved heat transfer in high viscosity fluids but are poor mixers. So the main objective of this kind of agitators is just to improve the rate of heat transfer rather than any kind of mixing that could occur. Okay, so that is the reason these are not rotated at a very high speed. So if they just move closer to the wall of the vessel at a low speed, so that itself sufficient to get the required objective achieved, that is scrapping the vessel to prevent the deposition so that the rate of heat transfer between the heating media and the liquid inside the vessel will be higher. So they are generally poor with respect to mixing action. The other two types of paddles, that is gate and anchor type of paddles, sweep the entire peripheral area of the vessel, walls as well as the bottom. So this kind of designs are capable of scrapping the entire periphery of the inside wall of the vessel. So you can see that the blade has extended towards the wall, also is closer to the bottom wall. So that way we can achieve the required objective of scrapping the surface of the agitated vessel. Okay, so some of the real pictures of the paddle agitators. You can see the different kinds of designs here. So this is an anchor type, this is an anchor with gate, and this is a gate type. Flow patterns in agitated vessels. So let us now take up in deep about the flow patterns that are generated in agitated vessels. So generally, the agitated vessels are meant for bringing the entire mass of the liquid inside the vessel to come in contact with all the portions of the liquid. So it is very important that the agitation is done such that the entire mass gets mixed up in a suitable manner. So if a suitable flow pattern is created, then only the mixing of the liquids will occur properly. So let us understand what are the factors on which the type of flow pattern that is created in an agitated vessel results. Okay. So that basically depends on the type of the impeller, then the characteristics of the fluids, size and proportions of the vessel, and also baffles and agitator. So all these are the contributing factors to generate the required kind of flow patterns in agitated vessels. The velocity of the fluid at any point in an agitated vessel has three components, namely radial, longitudinal, and tangential. So the velocity is a combination of these components. So depending upon which component is dominant, the type of flow pattern is created. So if the radial component is stronger, then it creates a radial flow pattern. Then if the longitudinal component is stronger, then it creates a vertical current, that is axial flow current. Then if the tangential means these are the components that act in the direction tangential to the rotational flow. So or a circular flow, okay, what you can say. So these currents, if stronger, then it creates circular motion inside a agitated vessel. The overall flow pattern depends on the variations in these velocity components from point to point. The radial velocity component, that is the first one, acts in the direction perpendicular to the shaft of the impeller. So the currents produced will also be perpendicular to the shaft of the impeller. The tangential or rotational component acts in a direction tangent to the circular path around the shaft. So these are capable of creating circular flow currents which are mostly undesirable. So with the vertical shaft in the vessel, the radial and the tangential components are in a horizontal plane and longitudinal component is vertical. So that is the reason the longitudinal component helps in creating axial flow and the radial and tangential flow currents components help in creating a radial and circular motion of the liquid. So both the radial and longitudinal flow currents or components are useful and produce the required kind of flow pattern for the mixing action to take place. If the given shaft is vertical and located at the center of the vessel, the tangential component is generally undesirable since it follows a circular path around the shaft and creates a vertex at the surface of the liquid and tends to continue. So this is what is the problem with the tangential component. Okay. So if you are locating the agitator with its shaft vertical located at the center of the vessel, then the tangential component, if present in a greater extent, it creates a circular path around the shaft. So that circular path is undesirable, is not expected to occur because that creates a vortex at the surface. That is, the surface of the liquid takes U shape and later on V shape. So that results in the entering of the air towards the center of the impeller and that leads to insufficient or inefficient mixing of the liquid inside the agitated vessel. So it is understood that the tangential flow currents are undesirable. So in circulatory flow, that is a kind of flow created by the tangential components, the liquid flows in the direction of motion of the impeller blades. So if the impeller blades are rotating like this, the direction in which the impellers are rotating, along that direction the flow currents are created. So that is a kind of circulatory flow that can take place in a agitated vessel. In case of unbaffled vessels, circulatory flow is generated by all types of impellers. That means, irrespective of the type of the impeller, the circulatory flow or a swirling flow is likely to take place if the given vessel, the agitated vessel, is not provided with the baffles. When the swirling motion is strong, the flow pattern in the vessel is virtually same irrespective of the design of the impeller. So at high speeds, the vortex is deep and may reach the impeller. So because of this, air or gas from the top of the liquid surface is drawn into the content of the vessel, which is not desirable. Okay. So when swirling formation takes place, if the speed is kept high, then the vortex shape will be very steep and it has actually creates in the very deep kind of a vortex that reaches the impeller. Okay, the shape of the vortex almost reached to the center of the impeller. So because of that, you can expect that air or gas from the top of the liquid surface drawn into the content of the vessel, which is not desirable because if that happens, then it creates a very large fluctuating forces on the impeller blades and that could damage the impellers. So in this diagram, you can observe the different kinds of flow patterns that can be obtained in an agitated vessel. So if you look at the first diagram, you can see that it's a unbaffled tank. We don't have the baffles fitted on the walls. So also, since the agitator is mounted at the center, you can see that the rotational flow or the circulatory flow in the direction of the motion of the impeller blades is created like this, and that creates the vertex formation in the agitated vessel. So if due to the entering of the air from the surface of the liquid into the vessel occurs due to circulatory motion, then the surface of the liquid takes a shape of U like this, and at a very high speed this shape will be almost like a V shape like this. So that means the vertex almost reaches the center of the impeller, which is a serious condition and it is not expected to occur. So the two types of flow patterns that are created in the second and third diagrams are the desirable flow patterns. Okay, so in this diagram only one impeller is used and you can see that it is creating a radial flow current. So a suitable flow current due to the presence of the baffles is created here without any vertex formation taking place at the top. So similarly, in the vessel where you have more than two impellers located on the same shaft, also we can see that the desirable kind of flow currents are created without any formation of swirling motion and the vertex formation. So these are the another set of diagrams showing you how the flow current or a flow pattern changes with the kind of mounting of the impeller inside the agitated vessel. So this is the first diagram where the impeller is mounted at the center and there is no baffle here, so due to which the circulatory motion has taken place that results in the formation of a U-shaped surface to the liquid that is getting agitated. So this is what is known as vertex formation, so which is not desirable. So here instead of keeping the impeller at the center, you can see that it is being mounted on the side of the vessel. So here even though a small vertex is formed here, so that is not very deep and it is being cut down by the currents, axial currents that are being generated. So this is another method of preventing swelling and vertex formation, that is by incorporating baffles in the agitated vessels, so that the flow currents, the circulatory flow currents that can be created will be broken down by this set of baffles. In that way the required flow current can be created. So in fact it is an axial flow current that has resulted. So in this diagram we can see the radial kind of flow currents without any swirling and vertex formation. So in these two diagrams the baffles are helping in avoiding swirling and vertex formation. And here the off-center mounting of the agitator has helped in avoiding circulatory motion and the creation of swirling and vertex flow pattern. Okay, so one more diagram showing you. So this is the axial flow and this is the radial kind of flow. This is a circulatory motion. The different types of impellers are used, means we can expect that different kinds of flow patterns to be developed in a agitated vessel. So that's all for today. So in today's class we understood the construction of paddles and how they are operated and what for and in which cases the paddle agitators are desirable. We also discussed in detail the different kinds of flow patterns that can be created in agitated vessels. So we learned that it depends upon the type of impeller, the dimensions used in the agitated vessels like the diameter, baffle design, then the other aspects, and also the type of liquid that is used in agitated vessels. So all these are the factors on which a particular flow pattern is created in an agitated vessel. Okay, so now the time is to go through a set of multiple choice questions. So the first question coming up for you is, paddle agitator is suitable for mixing low viscosity liquids, produces axial flow, moves at a very high speed, none of these. So if you can remember the things discussed, so then you will know that the paddle agitator will not move at a very high speed. and also it is not the one which can create a strong axial or radial flow current. So it is suitable for mixing low viscosity liquids is the right option. High viscous liquids and pastes are agitated by propellers, turbine agitators, multiple blade paddles, none of this. Okay. So propellers and turbines are not suitable for a highly viscous liquids or the thick pasty masses. Okay. So to agitate such kind of materials, the most suitable type of impeller is the paddle impeller that is provided with a multiple blade. So option C is the right answer. During agitation of liquids, power consumption during the laminar flow is not proportional to density of the liquid, viscosity, cube of impeller diameter, square of rotational speed. So at laminar flow, it does not depend upon the density. So it depends upon the diameter, rotational speed as well as the viscosity. So power consumption during turbulent flow, an agitation tank is proportional to the viscosity, thermal conductivity, surface tension, density. So turbulent flow, so the power consumption depends upon the density of the liquids. The blades of these dash agitators are usually vertical and extend close to the vessel wall. So out of the three types of impellers, we have seen that the blades of the paddles are the one which are having a similar shape as the vessel wall. So they are the one having the blades that extend close to the vessel wall. Dash are very useful in preventing deposits on a heat transfer surface as in reaction vessel and are commonly employed for obtaining improved heat transfer in high viscosity liquids. So the options are, sorry, forget about these words, they come up by mistake. The options are anchor type paddle agitators, bladed disc turbine agitators, propellers, core bladed turbine agitators. So it is the anchor type of paddle agitators that are useful in preventing deposits on a transfer surface and commonly employed for obtaining high heat transfer rate. So with that, let me end the session. So thank you for listening. So we will discuss more about the agitation operation in the next class. With that, thank you.